Mighty fine good day, everybody. My name is Cale Harbor of Advanced Control Solutions and Automation. Together with our partner companies within the Applied Automation Group, Olympus Controls and Gibson Engineering, we're excited to have you join us for today's discussion of the transformation of machine vision with deep learning. Our speaker today is Shweta Kabadi of Cognex. Shweta leads the deep learning software and electronic market solutions businesses. She led the product marketing function for Cognex's first deep learning software acquisition of ViDi Systems in 2017, and also oversaw the integration of Cognex's second deep learning acquisition of Sualab software in 2019. It is now my pleasure to introduce to you Shweta Kabadi.
Thank you, Cale. Good afternoon, everyone. I'm very happy to be talking to you today about deep learning. I've had the privilege of managing our deep learning software business at Cognex for the past few years. As many of you know, Cognex has been in the machine vision industry for the past 40 years, and it's exciting to see what deep learning technology is bringing into factory automation space, especially in conjunction with traditional machine vision. So I'm going to share a few my materials, just a second. All right. So today, I'm going to spend the next 25 minutes talking a little bit about why machine vision is hard, what is deep learning on a high level, how does deep learning work with rule-based, what opportunities is deep learning making easier in industrial factory automation, and how deep learning technology is evolving. So let's start with why machine vision is hard. Let's take this example. These images show visual inspection task for contact lenses. Now, everybody who wears contact lenses agrees that the lenses need to be 100% free of contamination and defects, simply flawless. After all, you're placing them in your eyes every day. But in order to guarantee that, a number of checks for contaminations, etch chips, holes, orientation, etc. need to be performed. Let's look at each image separately. Image number 1, there's a dot in the center. Is that a contaminant, a hole, or a benign air bubble on the top of a lens? The second one, you might be able to see there's a faint dot in the center. I don't know how it's coming through in the screen or not, but that begs the same question. How do we think about that? The third image, if you look at the inner circle, has a little chip at the bottom. Now, is that chip big enough to reject the lens? What about the fourth image? Now, that one looks kind of fine, but we probably need to measure the diameter of the lens to see if it is within the acceptable tolerance. Image number 5, there's another dot, but now at the outer edge. Number 6 has a small dot in the center, but again, this dot looks different than the one in image number 5. Image number 7 has 2 dots and a significant chip. Well, this lens clearly is going to have issues. And image 8 has another dot. These are just some of the defects that may show up. Now, let's talk about how somebody might go about solving this problem in factory automation. Now, of all the checks that need to be done, one was to precisely measure the diameter of the lens and verify that it is within a specified limit. Well, this can be a challenging task depending due to the fact that the lens is flexible and may be suspended in some kind of liquid, but there are machine vision algorithms that can do this. Another check was to read the code on the side of the lens. Again, this is something that can be done in machine vision algorithms. But what about some of the other checks? This image shows a potential edge chipping. However, there is no simple rule that can be applied to determine whether this is actually a defect or a chip that's acceptable. Similarly, in this image, you may wonder, this little black dot is actually a contamination inside the lens or just an air bubble in front or behind the lens. It's hard to apply a simple rule to do this inspection. Now the inspection using rule-based is getting really hard. But you know what? Humans can easily detect these defects much easier than traditional machine vision can. Now let's talk about, now that we know, and everybody pretty much agrees that machine vision can get hard really quickly, let's talk about what deep learning is. I find the terms artificial intelligence, machine learning, and deep learning being used quite interchangeably, but there are differences. Artificial intelligence is a broader term that refers to machines that do something smart and human-like. Machine learning, a subset of artificial intelligence, allows for a set of statistical methods that crunch data in a variety of ways to draw patterns, and then use these patterns that are understood on new data to predict outcomes. Deep learning, which is a subset of machine learning, takes it even a step further. It uses the data presented to it to discover and determine features on its own using neural networks. Let's look at it another way. How does a child learn? If I ask a little girl to draw an image of a house, I don't need to give her rules to do so. All I have to do is to show her a variety of different houses. And the child visually explores the world, the houses in this world, and looks at the houses and makes her own synthesis and determines what a house may look like. She may even be able to draw a house on her own based on it. This ability to learn complex concepts from completely unstructured data, such as images, is what makes us humans different than machines. And this is the ability which is the underlying principle of artificial intelligence. Basically, artificial intelligence is trying to mimic human-like behavior. Now, artificial intelligence in general has been something that's been around for decades, even probably as long as rule-based machine vision. But over the past 10 or so years, there's been huge advancements in this area, particularly with the advent of deep learning. Now, I mentioned neural networks in deep learning. What are neural networks? Neural networks build up a human-like understanding from a series of increasingly complex primitives. It's a set of nodes with weights and thresholds that make sense of data. The deep portion refers to the layers in the network. AlexNet, which is a network that's shown over here, is a type of neural network that became really popular a number of years ago. And it was taking image data and discovering features from it and making determinations based on it. Today, it's become an increasingly complex topic of study, and many large organizations and companies are investing here. This is a similar technology that Google uses to find like pictures of dancing dogs or something on the beach every time you put in a word on the Google search. And every time you tag a photo on Facebook, you might be helping train their algorithms to get smarter. But most of these companies are using these networks for general purpose image finding or speech or text recognition. Using deep learning for factory automation requires a more specified approach. Now let's talk about how do we think of rule-based with deep learning. first of all, machines and humans are different but complementary. If we compare machine vision with human vision, we know that computers are very good at tasks such as localization, gauging, and code reading. On the other hand, there are tasks such as aesthetic inspection, anomaly detection, or classification that rule-based approaches can either perform not as well or become quickly very, very complicated. Humans, however, excel at these tasks. And that's why today there are still lots of humans performing these tasks manually in the production lines. These tasks have in common that they rely on the ability to combine and carefully balance many different visual criteria in order to come to a conclusion. Interestingly, humans performing these tasks have a very hard time describing what kind of exact approach and criteria they are taking if you ask them. You know why? Because they have a very simple mechanism to acquire it. They just learn. Now, again, to make the point, rule-based tools are best choices for these kind of functions. After all, precisely aligning a wafer die, or laminating a film on a display module is a task of rule-based algorithms and not humans. Source code reading, because a human can't read a code, well, at least effectively. On the other hand, let's look at some other tasks that could be better suited for human-like judgment of unpredictable features. Inspecting a weld and making a determination of its defect based on shape and formation. That can get complicated pretty quickly for a machine. Looking through a complex picture of nuts, mixed nuts, and quickly determining the type of nuts in there. Or even reading a difficult code or an OCR, or difficult OCR on a plastic packaging that a camera is having a hard time imaging because of the reflections. A human can quickly turn the orientation of the package and be able to read that code. So does that mean that machine vision cannot solve any of these deep learning target problems? Not necessarily. Let's look at these images, where we are looking at welds again and making a determination whether these are defective based on their shape and formation. Now, you can do this particular task with machine vision. You can use different filters to extract, somehow use all the information you have about the defect to program measurements, orientation, etc., and make some determinations. You need a lot of information and a lot of work to get there. And if anything changes in the type of defect or any of the presentation of the defect, you need to go and change your rules all over again to allow for that variation. However, this is a really easy task for deep learning based algorithms. As a matter of fact, this particular problem was solved by Cognex deep learning software by just learning from 20 manually labeled images. And I was able to handle a variety of different variations. Let's take a look at another one. Classification problem. Here you see images of the tops of different carton boxes, and you need to classify what kind of carton box it is. Can you do it with machine vision, rule-based vision? Possibly. You need to determine, you will need to determine the unique characteristics or detectors of each carton box type, extract those, and write rules to make a determination. With deep learning, you show the software or the deep learning algorithms few images of each carton type, and it learns how to classify those images. Now, if a new carton type comes along, it's easier to adapt. Again, you take a few images and add to that and let it run again. And it's ready to go. Unlike rule-based, where you'll have to write another set of rules to recognize the new carton. Another example is OCR, which is a very common use case in factory automation, because there's a lot of OCR to read in factory automation. Now, there are many machine vision algorithms that can read OCR fast, as long as characters are segmented and well aligned. But what if they are not? Deep learning can help with OCR that's difficult to read because of contrast, poor alignment, or if the characters are bleeding into each other. All they have to do is show it a few of these difficult examples to the system, let it learn, and it's able to make those determinations going forward. So deep learning can not only go after very difficult cases, but can make really, really hard machine vision cases very easy to do. Let's talk about some examples where deep learning may be used in factory automation. There we go. Let's look at the automotive industry. Now, automotive industry has been using machine vision for automating a lot of tasks. Let's look at some examples that are better suited for deep learning. Cosmetic inspections are hard because cosmetic defects vary a lot and are very hard to predict. They may show up anywhere, and nobody wants to pay money for a brand new car with scratches, dents, or smudges on the dashboards or the hubcaps. Airbag stitching is another aesthetic inspection that is a good target. Now, kitting and assembly verifications can be done with machine vision, but as configurations of items change very frequently on the production lines, it's easier to have a deep learning-based system learn these configurations rather than have different rules for each one. Welding is another one we talked about, which is a very common but hard inspection, a good target for deep learning. Let's move on to a different industry. Consumer electronics. Much like buying a new car, nobody wants to open a package of a brand new phone and find a scratch on the display. On the other hand, battery scratches can actually cause functional or safety issues, so they need to be inspected well. But again, these are hard tasks for rule-based because you need to think of writing all the rules of all types of scratches that can occur anywhere. Similarly, looking for components on a printed circuit board. Why is this better with deep learning? It is because a capacitor may be bent and present itself differently depending on what image you're looking at. And a rule-based will need to know exactly how the capacitor may present itself. However, you can train a deep learning by showing images of a few variations, and it's able to make those determinations. Food and packaging is another industry which has all kinds of inspections, going all the way from raw material inbound inspection looking for contaminants to packaging, inspection of caps and lids and seals. Lots of opportunities here. So we talked about a lot of opportunities that can make life easier with deep learning, but there are a few considerations. First, you need images. If we don't show the deep learning system what to look for, it won't be able to solve the specific problem you want it to solve. So you need to keep that in mind. Second, you need somebody who has a knowledge of the application to pick the right images to train the system. For example, if you want a deep learning system to classify certain objects, and you never showed it a single image of a particular class, it'll have a hard time learning how to classify that. And thirdly, deep learning algorithms are compute intensive and require high compute GPU-based systems to train and even to deploy and run. However, there are lots of advancements going on in deep learning software and compute platform to make these considerations easier to manage. Yesterday, we needed GPU compute intensive hardware for both training and deployment of deep learning systems. Today, you can train on a GPU-based compute, or sometimes even use cloud-based infrastructure for running your algorithms to train. But more importantly, you have today the flexibility of deploying it on a PC-based system or an embedded smart camera with some special AI chips that can consume a deep learning model. In fact, Cognex has both deep learning PC software and a deep learning embedded camera options today. But more excitedly, where is the technology evolving? The technology is evolving rapidly to get to a place where it gets both easy to train and deploy. It's evolving to a place where you can do both from a single system, possibly from an embedded smart camera. It becomes easier to look at just a few images, train on the system, and get it ready to go. Now that is a great vision for deep learning in factory automation. Any questions?
Yes, thank you, Shweta, for taking us through that and the basics of what deep learning is. We've had a couple questions come through for the audience. Have you seen a common predominant application so far in using deep learning on the manufacturing floor that's dominated other applications?
We've seen all kinds. This one's kind of hard to predict, but one few that go across the board. We see a lot of OCR type applications because they are they're all over the place, difficult OCR, which was a little bit of a surprise to us because we didn't realize that was a great application for deep learning. Another one is welding, because if you think about welding, it's used across the industries, and that's another one. But no, we've seen all kinds of varieties of applications. Some of them have been like super surprising.
Okay. If someone were to have an application where they're looking at quality control, what type of information do you need to know to determine if it's a good application for a deep learning solution?
I think the first thing you need to know is there a lot of variation? Because what deep learning does well is managing variation. If it's very set standard, if you know exactly what the defect is going to be, what it's going to look like, and where it's going to be, you're probably better off writing rules for it. But that's really not 90% of the quality control, right? You end up having defects, you don't know where they're going to show up, and they may change. And when those kind of variations happen, that's usually a good target for deep learning.
Okay, great. That was all the questions that we had come in from the chat room to this point. Shweta, I'd like to thank you for your time today, for being willing to share your knowledge with us and the details about what Cognex is offering within the deep learning realm. To our audience who is attending with us today, I'd like to thank you for joining us. This session has been recorded. We will be posting it onto our YouTube channel, so it will be available for you to rewatch the event as be able to share with other people within your organization. I'd like to thank you on behalf of the companies with Applied Automation, Advanced Control Solutions, Olympus Controls, and Gibson Engineering for spending some time with us today. And thank you again, Shweta. Take care, everybody.
Thank you very much. Bye.